Welcome to the Lab 2 tutorial video of the COMP 2432 operating systems. And today, we'll be looking at the following objectives: the ownership model and scope, references and borrowing rules, thread and closures, as well as the channels and the interrupt signals. To make the introduction of this concept more accessible for you to understand, I will make the use of Ferris, the crab shown on the left, which is the mascot of the Rust programming language, to make examples to help you understand these concepts. Rust uses ownership to manage memory without a garbage collector. Every value has one owner, and when that owner gets out of the scope, Rust automatically frees the value. This prevents memory leaks and dangling pointers. Imagine you step onto the beach and want a shell from Ferris. Ferris gave the shell to you, and you own the shell while you're on the beach. When you left, i.e., you left the scope, Ferris took the shell back, and no garbage is left on the beach. Variables in Rust are immutable unless explicitly marked out mute. Immutable is just a fancy way to say that you cannot change it. It helps prevent accidental bugs. When variables go out of the scope, Rust automatically frees them, as you have seen in the previous sections in this video. Imagine you are given a normal shell by Ferris that is immutable. You are not allowed to make any change to it. You are not happy and want to get a mutable one. Then Ferris gives you a different type of shell that is mutable, say this conch shell for example. You are able to modify it, like changing its color. And when you leave the beach, i.e. you left the scoop, all your left shells are taken back by Ferris with no garbage left. Some types, like string, move when assigned to another variable. After a move, the original variable becomes invalid. Simple types, like integers, implement the copy trait, so they duplicate instead of moving. Imagine again, the shell that Ferris gave to you is heavy and expensive. Making a copy of it would be expensive, so you should just pass your shell to the next person who wants it. But when you are just given, say, a plastic bottle, which is cheap and lightweight, you can simply just copy it and give the copied ones to the other people. You are then both holding the bottles. Clone creates a deep copy of a value. Drop lets you manually free a value before it goes off the scoop. So, you are holding the expensive and heavy shell from Ferris at the moment. You just want to make a copy of the shell and give it to your friend. You can just use clone to do it. You and your friend will just get the same shell. A few minutes later, say your friend does not like this shell anymore and want to throw it away, you can just call drop to help your friend to do that. Rust allows borrowing values through references with the following rules. The first one is that many immutable references are allowed because they are read-only. Only one mutable reference is allowed. You do not want to raise the data. You cannot mix mutable and immutable references at the same time. Imagine you and your friend want the shell from Ferris. You can take photos of the shell, which are immutable, and you can duplicate the photo as many as you like. You can find out the exact location of the shell through clues showing these photos. You can interpret the meaning of references as these photos, pointing to the real thing, and can get you there, but they are just photos, not the real thing. But imagine now you have a magic photo of the shell, which also allows you to change the color of the shell remotely. This is called the mutable reference. You and your friend can only have one of this magic photo at any given time because you do not want to race to make the change to the shell, do you? Unexpected behaviors would occur if you both try to change it at the same time. You cannot hold the normal photo and the magic photo at the same time. Threads allow Rust to run tasks in parallel. Thread span create a new thread. Thread.join wait for the thread to finish. Imagine there's only one Ferris talking to you at the moment. With threading, you can have another crab greeting to you at the same time. A closure is like a tiny function you create on the spot, but unlike normal functions, Clojure can remember things from the place where they were created, move keywords, tell the clojure to take ownership of the captured values. Let me make an example for you. Say, Ferris like eating pizza. Do not ask why a crab would like pizza. It is probably a Italian crab. He wrote a recipe for making pizza and prepared all the ingredients needed for other crabs to make the same pizza. Ferris put the recipe and ingredients in a box, in this context, the clojure, and stored it. A few hundred years later, when the grandchildren of Ferris found this box, they can still make the same pizza Ferris did a long time ago with the recipe and the ingredients Ferris has put in the box. Channels allow threads to communicate safely. In the code below, TX means sender, whereas RX represents the receiver. Imagine it is like a phone line between two crabs. Multiple producers can be created by cloning the sender, so a rich crab can have two phones to send messages. Rust can listen for OS signals like SIGINT, which stand for signal interrupt, which is essentially the Ctrl-C event. Signals store forever loops indefinitely, receiving signals as they occur. Imagine Ferris sits with a radio headset. Every time someone presses Ctrl-C, Ferris sends a message through the channel. You can handle Ctrl-C in a separate thread, so the main thread is not blocked and can continue running. The signal listening thread sends a message when Ctrl-C occurs. Say Ferris wants to dance and does not want to listen to the event, so Ferris asks another crab to do the task. That is all for now. Thank you very much. I hope you liked it, and I hope this can assist your understanding in Rust programming. Please make an effort to understand the core ideas and processes involved in the optional reading materials, and feel free to reach out with questions to us through emails or the student form on the Blackboard.